So, the basic design of this wrapper is similar to what we have previously. So, 1500 wrapper. So, 1500 wrapper previously for the SOC testing. So, we could wrap the core. So, we have to consider this scan chain and input outputs of this core and put them onto this wrapper scan chain. So, we have to somehow design the wrapper so that we can it can be applied in serial mode, parallel mode and all those things. Now, that problem gets extended further, because for testing the router also I need to put it into a wrapper. So, since this core and router, they become an integral part in any system. So, they are taken together and this entire wrapper design is done taking both of them together. So, this core and router, they can talk to each other. There are signals connected through the local channel of the router, the core is connected. Now, it may have a number of scan cells here, the boundary scan cells. Similarly, this router will also have some boundary scan cell. So, they may be connected in a scan chain fashion like this. Now, from adjacent cores, this input will be coming. So, that will get that the unpackaging will be done. So, this is basically the job of this network interface module, and after that, so this may be for the router or it may be for the core. So, if it is for the router, then it will be coming to it will be coming to this part and it will be loaded into the router, or if it is from for the core, then it will be loaded from this side, it will be loaded onto this part, or it may be done serially through this. So, there are many options that are created. So, on top of the 1500 compliant wrapper, so this test wrapper has to be designed. It should wrap both the router and core. Packing and unpacking mechanism is reused from the mission mode. So, mission mode means in the functional operation of the system, there is the network interface module which does this packing and unpacking. So, here that part will be that part of the hardware will be reused in the test mode. So, it is modified to work in a different fashion. So, this test patterns will be it will be selecting this unpackaging mode. So, it will select this one. So, it will make the test pattern to go through this channel instead of the functional input being fed from this side. So, test pattern will be fed from this side. So, that will be loaded and these responses will get collected and the responses will be transferred to this one, and then it will be going to the next package. Because now this part works in functional mode, because because this the test pattern and responses have been collected from this particular core. So, they are to be applied to the next core just to transfer to the destination. So, rest of the thing they operate in the normal mode, only this core and router, they will operate in the test mode. So, this shows the detail in mission mode of operation. So, this router is from adjacent core. So, we will get this input coming here, and they are actually from the router, they will go to the adjacent core. So, basically this router has got function, like it may have some data that has come from the neighbor. So, if we look into a mesh router, so if this is a mesh router, then it has got a number of neighbors. So, this is top neighbor, this is left, right and the bottom. So, these neighbors are there. Now, it has got a local port as well to which the core is attached. Now, when a packet comes to this router, so it may be from these neighbors, okay, or it may be from the local port. So, whatever it is, so it has to transfer it to the next step. So, like here, so if it is coming from if these are the 4 channels coming from adjacent cores, then it has to send the data to some adjacent core depending upon the address requirement. So, it may be the data that is coming from this left has to be routed to this top. So, that has to be done. So, this way this router will be doing this routing operation. So, it will be done there. Now, this and for the core part, so for the core part, so it will be doing this unpacking and packing. So, if there is some data destined to this core, so it will be going to this unpacking mode, and then it will be coming to this core. And similarly, if this core is willing to transfer some data, so So, data has to be packed first. So, it goes to the packaging unit, that network interface part. Actually, this unpacking and packing, so these two modules are together forming the network interface part. So, they are actually the network interface part of the system. So, so between core and router we have got this network interface module. So, from core whatever message has to be transferred, so that is coming to this NI network interface packing module, and then it will be doing the packing there, and that will be given to the router for transmission to adjacent cores. Okay. So, and if from some adjacent core it gets some packet to be delivered to the core, so it will be going to this unpacking module of this network interface. It will do the unpacking, and then the data will be delivered to the core. So, this is the normal operation or mission mode operation of the wrapper. Now, in the test mode, so it changes, because in the test mode, so this data comes from the serial input. So, like here, so from the testing from this data that is coming from this core, so that may be used for from the adjacent core, which may be the test mode, which may be sending the test pattern. So, it will be loaded into this chain. So, instead of being delivered to the router for transmission to the next one, so it will be delivered to this chain, so that the test pattern gets loaded, and this test pattern gets applied to the router and core, and the responses are collected and then transferred to the next level. So, this way the same module can be used for mission mode operation and test mode operation. So, for the test scheduling problem, so we can do it like this. So, first of all, so this is again a heuristic algorithm. So, this is not an exact one. So, heuristic algorithm. So, what it does, it permute cores in the order of test time. So, so we arrange the cores in terms of their test time, whichever core requires highest test time. So, that is done first, and that way, and permute all input output pairs. So, we try out some IO pair permutation, and for each permutation we find some free IO pair. So, we take up the first core and see whether any IO pair is free or not, check for resource conflict, schedule the core. Now, after scheduling the core, we need to have this thing, that routers on a path should be all tested before functional cores on that path to be tested. So, this is the additional thing that is ensured. So, if you take this routers and cores as two integral module, and all of them are to be tested. So, and there is a precedence relationship, we can say that it gives rise to a precedence relationship between the test modules, that is the router testing should be done, for all the routers on the path should be tested first, then only the cores on that path can be tested. So, this gives rise to some precedence constraint, and then we can use this constrained test scheduling problem that we have seen previously. So, in the SOC testing part, so that can be utilized for doing the testing. Okay. So, of course, with the modification that now it has to go through these routers only. Routers can be tested concurrently with cores. So, this is possible. So, whenever we are testing one router, one core, so we can test more routers, because they are not going to conflict. And this one, if we assume that the router responses are evaluated locally near the router, in that case we don't have we don't need to transfer the router responses to the IO, to the output port. So, that way it will give rise to saving. Okay. So, at least one IO pair should be used for router testing at any time, because I have to always do that router testing continually to make this code testing problem proceed. Okay. So, to proceed through the stages, so I need to have this router testing done continually. So, this is the thing that we have to have one IO pair dedicated for testing the routers. So, this is the integrated test scheduling problem. So, it says that all these routers are tested, one of the two IO pairs can be used for testing. So, we are first this input 1, there are two IO pairs, input 1 and input 2. So, since these are the channels through which the test will be done, so if we are proceeding like this, then all these IO pairs are these routers are to be tested, whether if this is for the multicast situation, this is for the unicast situation, but whatever we do, so we need to test the routers on the path. So, all these routers are tested, one of the two IO pairs can be used for code testing. Now, channel width utilization, if we see, then so if we have situation like this, that if the channel width is say 16 bit, so we say the flits per second. Actually what is happening is that if we have got say if we have got a packet P between one router to the next router, I have got a number of parallel lines. Now, in one time unit, so how many bits we can transfer? So, that is equal to the width of this channel. Fine. Now, if the width of the channel is say 16 bit and a packet has got say 32 bit, that means I have to transfer it over two successive transfers. Okay, or to send the packet over two successive transfers. So, this is known as fleet. So, in one clock how much data you are transferring. So, in NOC terminology, so that is called a fleet. So, we have got something like fleets per packet. So, per packet how many fleets are necessary, and we know that this transfer is taking a fleet, and one fleet takes one clock cycle to traverse through a link, and depending upon the router design, one fleet may take 1 to say 5 cycles it would go through the router. So, that depends on the router design, but that is known at the time of design. So, you see that if we have got say 24 packets, then the fleets per packet is 2, and in this case the test cycles needed for this one is 38. So, this is basically after taking care of this overlapping this parallelization and pipelining of packets being transferred and all that. So, it can be computed, so that is equal to the 2, because in one 16 bits will be transferred and the next one is 8 bit, but 8 bit will be transferred as 16 bit. So, this requires 38 clocks test cycles. So, this is similarly if there are 146 packets in for core 2. So, there are 13 fleets per packet, and this is the number of test cycles. Whereas, for channel width 32, so we have got the corresponding figures like this. So, since the channel width is fixed, okay, so between two routers the channel width is not flexible, unlike this SOC testing where the TAM width may be flexible, may be fixed, and we have seen that making the TAM width flexible could reduce this test time significantly. So, that way that option does not exist in NOC testing. So, channel width is fixed. As a result, there will be lot of channel width that is not fully utilized, like here the first time I am sending 16 bit, but for the next time I am sending only 8 bits, but I have to have data for 16 bits in the second case as well. So, how can we use this idle channel width? So, we can have some variable on chip test clocks. So, this on chip test clock, so if it can operate at different frequencies. So, we use faster wrapper test clocks on cores with idle channel width. So, they have got idle, the channel is remaining idle. So, we can transfer more data, more test data onto that time. As a result, so these cores they will get more test patterns in shorter time. So, this can be useful, this can be done, and we can use this idle channel. So, if the channel width is W and this wrapper scan chain width is W dash, n fleets can be transported in parallel to core in one clock cycle, where n is equal to W upon W dash, because wrapper scan chain width is W dash. So, that means in one transfer I need only W dash bits. So, if I have got if the channel width given is W, which is so for example, if say W equal to say 32, okay, and this W that is the channel width from the channel width of the NOC, and for a particular core this wrapper scan chain width say W dash equal to say 8. Okay. So, that means, so I can transfer so 32 by 8, that is 4. So, 4 number of fleets can be transported in parallel. So, that way the destination it will receive more amount of test data per unit time. So, if the destination has got if the core can be tested at a higher frequency, then this can be used for that. So, additional cores can be selected to further reduce test time. So, you can also say that in this test time I will not be transferring test pattern only for this core, but for some other cores as well. So, it actually violates to some extent that reservation policy, that is the resources are reserved for the test session of a core, but it is that violation is there, but at the same time it saves the time, it saves the transfer time for the other code. So, that way so we use that other code data to be transmitted while while we have got idle time for the first core. So, this way we can utilize the idle time of the channels. So, this is the situation. So, this tester, so this slower tester clock can be given to the wrapper, and then we have got a phase locked loop which is on chip. So, that generates from this slower clock. So, it generates some faster clock, and this faster clock. So, this wrapper is operating at a faster clock compared to this wrapper. Now, the test pattern, so that is being transferred from this tester, the test data that is getting transferred. So, it can be transferred to this wrapper at a slower rate, because it is operating at a slower frequency, whereas for this wrapper, for this wrapper, the test data can be coming at a higher rate. So, between so from core A to core B, the if the test patterns are going to be transmitted, then through this network channel. So, this is 4 bit. So, that way it is going to the router of the next level, the 4 lines. However, here it is operating at a higher frequency. So, more number of test bits have can come to this core B, and this wrapper by doing a multiplexing. So, it can take care of this, because at for some time. So, it can send the data through the select line. So, it can send the data from this router data, it can be sent through this multiplexer to this wrapper chain, or it can be so either of these two lines can be sent to this wrapper chain. So, if that more data has arrived here, then they can be transferred using this clock to this channel, okay, to this individual bypass cells, this buffer cells. So, we use slower wrapper clocks on cores with high power dissipation, and then naturally no change on the wrapper design policy, but physical channel can be viewed as n virtual channels now. So, physical channel, so this is the tester clock that is applied. So, packets in channel are like this, A B C, first A B C like that. So, this so test clock on core A is applied as in this way, that is it gets the core for it gets the test pattern for A, and so whenever this A pattern comes, A packets are put onto the channel. So, test clock is given to core A. Whenever B packets are put, so this is given on this clock is given to core B. So, this tester clock, it is from this we derive 3 clocks, this test clock for core A, test clock for core B, and test clock for core C. So, this tester clock is high frequency. So, it is putting the test data for these channels A, B, C one after the other onto the channel in a multiplexed fashion, and then on the at the tester, at the individual cores. So, they are sampled at their own frequencies. So, as a result they get their original test patterns. So, physical channel that we have, so it is viewed as a as n virtual channel. So, if there are n number of core test data that is being sent over the same channel here, then that is basically n virtual channels are created. So, all those n channels are getting data simultaneously, and as if as if they are getting the data simultaneously, and they are getting sampled at the corresponding clocks. Next, we will look into another very important issue, like how to handle this power hour test scheduling problem when we are talking about this testing of this NOC based system. So, we have got say n cores, and the tester clock is FT, we can have some faster on chip clock 2FT, 3FT, etc., and there may be some slower on chip clocks FT by 2, FT by 3. So, these are the derived clocks from the system clock. Then the test policy or the test scheduling policy, it is not only determining the assignment of cores to IO pairs, their schedule and all that, it also needs to determine a clock for each core. So, which core has to be tested on at which clock, such that there is no resource conflict, that is the first thing. Then the system test application time is minimized. So, overall test time gets minimized and power constraints are not violated. So, power constraints are to be taken care of. So, so these are the three things to be done, and that is actually the power hour test scheduling problem. So, each core has got associated with it a set of on chip clocks. So, so we have got it is assumed that all these different clocks are available, and this is actually done in the design at the design time. So, designer might have derived a number of clocks. It is normally not the case that for testing we use a number of derived clocks. So, whatever derived clocks are available from the design side, so we have to use it. So, if it is the case that so many derived clocks are available, 3FT, 2FT, the FT is the normal rate, then FT by 2, and these are the slower clocks, this is the faster one. Then each clock corresponds to a power Pij and the corresponding test time Tij, because the power consumption, the dynamic power consumption is proportional to the frequency. So, as frequency increases, the test power consumption also increases. So, we have got this clock. So, for every clock, so we can find out what is the corresponding power consumption. Similarly, if you are testing at a higher frequency, the test time will be less, because it will be able to apply more number of test patterns in a shorter time. So, that way the test time will get reduced by a factor of this higher frequency rate, and this way and on the other hand, if you are trying on a slower clock side, then this power consumption will be low, but this test time will also be high. Now, selection of clock of each core is controlled by a priority calculated by delta p by delta t. So, delta p is if you go to that particular frequency, what is the increase in the power consumption, and delta t is the what is the increase in the time requirement. So, this ratio if we take, then if some core has got a very high figure of delta p by delta t, that means it does not it requires lot of power to be consumed, but without much saving in the test time. On the other hand, if this value is low, that means it is it may be possible that it is requiring very less amount of power increase, but at a considerably high saving in the test time. So, that way this delta p by delta t can be used for selecting the cores, selecting the core and the clock frequency for a core. And more than one cores use slower clocks to utilize virtual channel. So, this is other possibility. So, we use more than one core to use the same slower clock in a using the virtual channel facility. Okay. So, this that can we have seen the virtual channel concept that can be used. So, that is possible. Then another possibility is that use dedicated routing path. So, we can have some so instead of putting all traffic onto one side, maybe we will put some dedicated path for the individual core testing, and that way for XY routing it is definitely dedicated, but if some other routing policy is followed, so it may be that for some part of the router, some part of the network, if we find that it is going to be used very frequently, then we may try to reduce the load on that and try to give some idle time for that path and give it to some other path. So, this way we can put some time gap and on that path, that way so dedicated routing path can help us in that way. Power constraints are definitely to be evaluated. So, power hour test scheduling tries to address all these issues.